Okay, these are the problems that I gave you that were in that packet. We're going to go through all three of them. I'm going to just tell you up front, this is going to be a little bit raw, but you should be able to get through it. So this is the first one that we're looking at here. So we've got Nawaz and Narendra are attempting to solve this problem in their textbook. Ong is riding her bike. For the first hour and a half, she cruises along at 10 kilometers per hour. Then for the final 20 minutes, she really pushes it and goes 25 kilometers per hour. What was her average speed? If you were helping Nawaz and Narendra, what would you do before anything else? The first thing you need to do is convert everything so it's in the same unit. So meters in seconds or kilometers in hours. If you wanted to do it into kilometers in hours, there's nothing wrong with that. It's up here. That would be 10 kilometers per hour, 1.5 hours, and then 25 kilometers per hour, 4.33 hours. So 20 divided by 60. All right. In general, most of the time you're going to have to, if you're going to have to do that conversion, you're going to have to do it into meters and seconds, which is what I did there. So the way I did 10 kilometers per hour to meters per second is here I converted the hour into seconds, so 1 hour is 3,600 seconds, and then here I converted the meters into kilometers. So that would give you a total, when you multiply across the top and divide by the bottom, you would get 2.8 meters per second for a total of 5,400 seconds, which is just the time, which was 1.5 hours times the number of seconds in an hour, 3,600. Okay? And then I did the same thing on the other side. I did 25 kilometers per hour into meters per second and got 6.9 meters per second, and a total time of 1,200 seconds. So we need to remember these two things here. This will come back in handy in a minute. All right? So we're going to keep those things in mind. Now, Nawaz suggests that the way to do this problem is to average the two speeds together, and Narendra suggests that you need to find the total distance traveled and the total time traveled, then find the average speed. So who do you think is correct and why? I can't really tell you what you put, but the person you should have put was Narendra. Narendra is correct because he is using the definition of average velocity. Remember, let me go to the next page. Remember, that definition is the average is equal to the total distance over the total time. Okay? So total distance over total time. So Narendra is correct. Why is the other student incorrect? Nawaz has fallen into a trap because it does seem okay to do that, to do what he said, to take your value for your speed, so 10 plus 25, and then divide by 2. It seems like that would be okay. The problem is that Ong is using those speed for different amounts of times and different distances, so it's not consistent. So that's the reason you always really need to be careful about that, and you need to do the total distance and the total time. Okay? So that's the reason Nawaz is wrong. More importantly, Narendra is right just because that's the definition of how to find average speed. Okay, so could you use a graph to help solve this problem? How? You could use a graph. You could graph the velocity versus time, and then find the area under the curve to get the total distance. So let's say that this is what you did. You got velocity versus time, and then 1.5 hours, and then 2. So you could graph something like this where you had 10, and then up to 25. Just pretend that's 25. I can't write it small enough. Alright, and you could do something along this line where you have it going 10 to 1.5 and then up to 25 for that last 20 minutes. And then all you'd have to do is find the area under that curve, and that would give you the total distance traveled. And then once you got the total distance traveled, you would just divide it by the total time traveled. Okay? So that's how you could use a graph. You could also, I suppose, I saw this somewhere, one of y'all did this, I suppose you could do something like this where you have the distance and time graph, and you go ahead and figure out the exact distance it goes in the first bit, and then the last bit. Hang on one second. First distance it goes here, and then she's going to speed up, so it's going to be a little bit steeper. And then you could just use this, and you could find the average speed using that line. So like figure out where you got here, that point, and you could just do distance over time there. You could use that if you wanted to. Alright, so the last part is how to solve the problem. So right here I showed the work to find the distance traveled in the first time interval, and then right here I showed the work to find the second time interval. Alright, and so after you find those two distances, you then can add them together, and you add the times together, and then you divide. Okay, so you're just using v equals d over t, and then solving for d, okay, for both distances. And then once you get those distances, you then can use your average velocity formula, total distance over total time, and that should get you the answer. This is the answer. I think I got it right for kilometers per hour. I did that one more in my head, so if it's wrong, let me know. Okay, so that was the first question. The second question, Macron and Modi are designing a lab to determine whether a car is moving at a constant speed. Macron thinks that they should proceed as follows. 1. Measure the distance a car goes and the time it takes on a given path. 2. Repeat several times for the path, and then solve for velocity in each instant. If they are the same, or roughly due to error, then the car is moving at a constant speed. Modi thinks the procedure should be measure the distance a car goes and the time it takes on a given path, repeat 2 or 3 times to ensure accuracy at the same distance, then change the distance and repeat steps 1 and 2 a few more times. Solve for velocity each time. If they are all the same, then you have a constant speed. So who is more correct, Macron or Modi? Modi is more correct because he is guaranteeing that the car's average speed is constant over different distances. So what Macron is doing is checking the average speed is constant in a given interval. So if we look at this interval, d, even if the car is moving at a constant speed, then that's great, but if they're accelerating, it would be the same each time. Alright? And you wouldn't necessarily be able to tell if you were doing a distance versus time graph. Let me show you what I mean with the dots. So I've got the dots here for constant speed. So notice, if you're measuring the same distance each time, if it was going at constant speed, you would see that result because the total distance over the total time would be the same. But what if instead you had dots that looked like this? That looked like this. Whoops. I'm going to put them here. Boop, boop. Okay, so now we've got dots that look like this. Notice here that if we do this interval multiple times, we would get the same result. We would still have the same total distance and the same total time every time. But if we did this distance and that time, we would get a different result. Or if we did this distance and the time associated with it, we would get a different result. So if you had just a single interval, you wouldn't necessarily get a good result because yes, you'd be checking to see if the average speed was the same for that interval, but you wouldn't be checking to see if the average speed was the same over a greater period of time. So again, the reason Modi is correct is that by changing that distance, you ensure that you are getting an average speed over the entire course of the experiment, instead of just over a single section. Okay? And then the last question says, draw a diagram that would display this object's motion if a detector could only notice a light blinking on the hood of the car. Well, if it's going at a constant speed, you should have evenly spaced dots picking up on that blinking light, just like we had in the lab. All right. Last question. Madiba and Nelson are trying to design a lab to determine whether the speed of a car is constant. Their teacher, Mr. de Klerk, gives them a strobe light and an old camera. How might Madiba and Nelson use the given equipment to determine the motion of the car? So this is basically the lab that we did. And all they're trying to do here, though, is determine whether the speed is constant, right? They don't need to know what the speed is. That's the key. So since we don't have to worry about what the exact speed is, we can just basically use those dots to determine whether or not it's going at a constant speed. So the way we would set this up is you would have your camera positioned in such a way that you could see the entire, the lines represent the view of the camera, you could see the entire course of the car as the car goes across. Okay? So you would do that first, then you would switch the lights off and turn the strobe light on, and then begin exposing the film when the car starts to move. And then as the car is moving across, you stop it once it gets out of frame. So once it reaches here, you would stop the film. And then after you got done with that, you would look at the picture. Alright? Nelson and Madiba determined that the car was moving at a constant speed. Show what the raw data would look like and what the graph of the data would look like. So the raw data, if it's moving at a constant speed, would be just evenly spaced dots. Okay? Those dots should be evenly spaced, and the distance and time graph should be constant. By the way, if you were looking at a velocity versus time graph for this, just FYI, it would look like this, a straight line, because the velocity isn't changing. If the velocity isn't changing, then the distance looks like that. Alright, so that is your answer to that one. If instead they found the car was not moving at a constant speed, show what their raw data would look like and what a graph of said data would look like. So here I've got two options. On the first one, we've got an object that's like speeding up and slowing down repeatedly. And so what I've done is I've shown it, you've got a lot of distance in that first interval, less distance in the second interval, more distance in the third, less in the fourth. So basically it's shifting back and forth between high and low speed. So it might look something like this, where the, let me draw it a little bigger for you, where the initial one is a steep slope, because steep slopes are associated with quickness, and then we've got a lesser slope, and then another steep slope, and then a lesser slope. Alright? So that's one option. Another option is to have the object accelerating. So if the object's accelerating, you would see greater and greater distances showing up between those dots, and the distance versus time graph would look as shown. It would be curved. So if you're accelerating, that distance versus time graph is curved. By the way, if you were looking at the velocity versus time graph for this, it would be a straight line because the velocity is increasing over time. And so this graph is associated with this graph. Alright? Let me check and see if there's anything else I want to update y'all on. Okay, these are just a couple of last minute things. I just flipped through the test. I wanted to make sure you remembered. You just need to make sure that you recall the difference between distance and displacement and speed and velocity. Okay? Remember that distance, let me draw two things for you real quick. If this is point A and this is point B, and this is the path you took to get there, then distance is the total amount traveled. So you just follow along that path, and whatever that distance is you might get, let's say that it was 50 meters, let me redo that real quick. Let's say your distance was 50 meters. The displacement, though, is the straight line distance and direction from where you started. So this might be your displacement, 35 meters to the right. Alright? So that's what displacement looks like. So displacement is how far you are from where you started, and distance is how far you went along the path. Speed, remember, is distance over time. Is distance over time. And velocity, remember, is displacement over time. If they ask you to make that distinction, that is the distinction. Okay? The last thing I'm going to remind you of is that if you have the dots, you need to make sure you remember that the flashes, the flashes happen in the gap. So the time between this flash, so like for instance here I've got 0.3 seconds per flash. So that means that each gap is representative of 0.3 seconds passing. So here we would have a total of 0.3, 0.6, 0.9, 1.2 seconds. Alright? So those are just the last minute things. If you have any questions, feel free to send me a remind or tweet me, or yeah, whatever you do with the Twitter. Alright, good luck.